Hi, my name's Dan, and in this video I'm going to show you how to create a program counter in DigitalWorks. So DigitalWorks is a simulation software for digital electronics, and a link to it will appear in the description down below. It's free software, so you can get hold of it yourself. So this video is part of a shorter series of videos in which we're putting together a 4-bit CPU simulated in DigitalWorks. Everything is quite specific to this particular design, and this short series is actually part of a much larger series which charts the progress from going from the basics of logic gates, putting them together to make this CPU. We're nearing the end of that stretch now, so if you've been with me all along, that's great. I hope you're enjoying the process of making this thing. I hope you're playing along with me and actually doing the making rather than just watching the videos. And that series of, I think it's 55 in total that there's going to be videos, is in turn part of an even larger suite of videos, which are my computing fundamentals tutorials, which are intended for use at Northumbria University for first-year students learning about the fundamentals of computing, which then in turn is part of an even larger thing, which is my channel, which has got a whole load of videos under several different subjects, all of which are kind of related to game dev, some more, some less, which then in turn is part of the larger thing of the YouTube, which in turn is part of the internet, and blah, 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 blah. You get where I'm going. So there's a roadmap also in the description below of where we're going in terms of this this medium-sized set of creating this 4-bit 4-bit CPU. And towards the beginning of this set, things were quite generic when we were creating registers and multiplexers and decoders and things like that. So the stuff that was dealt with there was very applicable across lots of different applications. But for the last few playlists, shorter series, we've become quite specific in terms of the design of a particular CPU that we're creating. And within this design for a CPU, hopefully you see what I'm doing. I'm focusing back down on this particular video. We need a program counter which has some special capabilities, which is that it is able to increment, which is add 1 to itself when it follows the instructions to do so. So a program counter is basically a register. So we're going to chuck in a 4-bit register. Where's my registers? And if you've been following along, you should have this set of parts. You might have created some more for yourself as well, and that's great. So I want a 4-bit register to throw in, and I'm going to put an annotation next to this that this is the program counter. PC for program counter. So there are some things that we want to make sure are done with the program counter, which is it needs to be bus ready. So we're going to connect it up to the bus. And we've got output enable that needs to be connected up and bus read that needs to be connected up. So we'll just make sure we've got those done and out of the way. These are just tags that I'm putting in, which then connect through to the template. If you don't know what I'm talking about, you need to work out how to use DigitalWorks. I'm not going to explain that every time I do a video. And then what's next? Well, we need to be able to do an increment to this. And in fact, the way to do that is to use an adder. And somewhere we have a 4-bit adder. There we go. And what we're going to do is we're going to link in, link the value through to A, which is one side of our adding. And we're going to add 0 to it, which may seem wrong because we wanted to add 1 to it. But what we want to do is to actually have control over whether actually we do increments, because again, if you've been watching through in the series of videos, if we do a jump command, then we want to not increment, but we just need to tell it that it's not incrementing. It will go through the same process, but it won't actually add one. So it'll come through the adder, but will come through unscathed in that case. But most of the time, we want it to actually add one. And the easy way to do that is to just use the cin, which is the carry in, which will add one. We could just use the lowest the lowest significant bit on B as well. That would work equally well. So what I'm going to do is I'm going to link up the B inputs to ground, which is what this symbol is, which actually is a permanent 0. And we're just going to make sure that this is a permanent 0, 0, 0, 0 that's being used. And then we're going to link up the cin, and we call it, on the output on the control unit, we call that inc, which means it's going to be high if we want to actually do the increment, which is most of the time. But if we've done a jump, it's been set to low. Let's stick some annotations in. So that's bus, and it's 3 to 0. Again, you should be getting used to this terminology and the way that I'm approaching this. I know it's just connected across and you can just look across to there, but I am going to label these bus read and output enable. And the justification for doing this is just a few seconds extra, is that when I then connect up these tags to the pins and the template, it just makes it gives me that tiny bit less to think about. And I'm gonna do that ink. Right, so what we want to do is we're going to have 2 stages, and the first stage is going to copy from this register through the adder, and we're going to use a second register. So let's find the 4-bit registers. 4-bit register. So the first phase, as I said, is going to go through there and is going to copy to this register, and then the second register, we're going to link the value output from here back to the data here. So the second phase is to copy that back around there. And this isn't going to be very hard at all, to be honest. Right, so we need to connect up the data. We don't need to do bus read and output enable. We don't need to connect up the bus because this is kind of a hidden register. I'm going to just to be in keeping, I'm going to call this the inc register, which the name clashes with that, but sometimes in CPU design you see these shown as separate entities, the PC and the inc, and sometimes incrementing isn't done using a bespoke adder like this. It can be done in other ways. And that tends to be the name that is used, the inc. Okay, so we need to connect this back around to the value, and we need to make sure we're connecting 0 to 0, otherwise, and vice versa, etc. Otherwise, we're going to have all sorts of interesting issues because the counter is just going to count wrong. A lot of the process of doing this seems to be just making sure the wiring is absolutely right. But once it is right and it's working right, it works as expected, or it should do. Unless you're expecting something unreasonable, of course. Right, so that's linked back around. And what else do we want? So we want to actually take in those control signals. So I'm going to put one there and one there. And in fact, they link up to data read. I've pulled them out further so they're a little bit more obvious, but I could have put them right up against the component there. Now let's get this right. So I've got two phases. Each of these represents one of those phases. It represents that when it goes high, there's a pulse come in. That is the command to do something. And we've got ink 1 and ink 2. I guess that's again slightly confusing with ink here. Ink 1 is the bottom one because that is where we actually copy from the PC register to the ink register and add 1 in the process, probably. And then ink 2 is copying it back to there. So that's the data read from here. It'll read from the data from there, which will automatically be using the value there. We don't need buses for this because it's a dedicated bit of communication. There's only these two things going on there. So ink 2, we have a space. And finally, I'm going to put one extra thing in here, which is when we start, before we get running, we want to make sure that we've set our program counter to 0, and I'm just going to use the clear on here. And there's no reason why I can't also clear the ink. It probably isn't necessary because when we do ink 2, it'll read from there. But so, but there's no reason why not. So we might as well have a bit of belt and braces in there in case something weird goes on. So we're just going to call that clear. Okay. And that's the gubbins of it. That should be working. Now we need to create a template so that we can turn this into a macro and use it in our CPU. So go to the template editor and it's a new day for me. So I haven't got something that's there from previously. Let's give it a name. We're going to call it PC. We could have called it PC and ink. Right, so what do we actually need to connect to the PC? We might be able to make this thinner. Well, we need the bus, and we need the bus controls. So I'm going to the wrong place. The tags are here. And I'm having a habit of putting the bus connections on the left-hand side of objects, because what I'm going to do is when we actually create the CPU, which won't be very long now, I'm going to put the bus down the left-hand side and put all the components that talk to it next to it. What do I want to call this bus? 3 to 0. And then I'm going to make that smaller. My labeling for the names for things, and on the main circuit I use 10 points, but labeling the pins on a template I use 7 points, just because I needed to make a decision about these things. So what else have we got? We've got the bus connection. We're going to need a bus read, an output enable, ink 1 and ink 2, and clear, and this ink thing. So that's 1, 2, 3, 4, 5, 6 more connections. And I'm just wondering how best to do this. Can I fit all 6 on one side? It might be a little bit crowded. No, what I'm going to do is I'm going to put the phase controls, so the ink 1 and ink 2, at the bottom. And the reason for that is, if you remember the diagram that I've got of the architecture, I'm probably going to lay the CPU out very similar to that diagram. And so the ring counter, which is the thing that sends out these signals, is probably going to be underneath everything else. And so having them on the bottom where those lines can come in from below is entirely reasonable. So that's ink 1 and ink 2. Okay, I'm actually going to move them a bit further over. I'm going to center them in there. And that leaves room for four more things down the side. So I'm going to do bus read output enable and the increment in and clear in that order. And I'll slightly change the order from what I said. Bus read. OE, because output enable is quite long. And clear. I'm going to put clear together with bus read and output enable because conceptually they're control, whereas this is data. And I'm also separating it slightly to give a slight visual hint that they're somewhat different. And so that's my ink in, not to be confused with ink 1, ink 2. Yes, okay. So that should be all the pins that I need. I'm going to do the wiring up. And sometimes at this point I do a fast forward and play some music. I'm not going to do this time because there's not that much to do. And I feel like keeping talking. Although what I'm going to talk about, I'm not entirely sure. So yes, let's say this. Then quite a lot of the stuff that we're doing now in this late phase of these videos is very specific to um, this CPU. This program counter, however, actually is quite universally useful. And the thing that's potentially slightly unusual about it is the fact that I've got two control lines coming in to do the two phases. Another way of approaching that would to actually be to put on ink 2 to put a NOT gate, an inverter in there, so that when not, and then to put the two together, so we would take an inverter off here and to go into there, and that would mean that when it goes, you could send it a pulse, and when it goes high, it would do the first phase, and then when it goes back low, it would do the second phase. I haven't approached things in that particular way on purpose, because it's just slightly more confusing when you start talking about doing active low stuff, which is what that is called. And I tried to keep everything similar. I guess the advantage of doing it with one command is that you only need to give one command, but um, that doesn't necessarily speed things up. I don't want to set. What am I doing? I think there we go. Because the way that I'm doing things is I'm kind of explicitly having separate phases, and my three things, which are uh, um, the fetch, the execute, and the increment, all take two phases, and I could have done them all using a leading edge and a falling edge. But all I need to do in this case is actually just run my clock twice as fast if I want to make it go at that kind of speed, and it's just more explicit this way. So I don't have the problem that I need to squeak as much speed as I can out of the hardware. Right there, that's connected up. We're going to save this. So save as, make sure we're in the macros, and this is a program. I'm going to call it PC for short, but PC register, so that we remember it's a register. And as is traditional, I'm going to do a new circuit and test it. So where are we? PC, PC register. There we go. Right, I have immediately realised that there is something that I haven't done and I haven't put on here that would be really useful to have, which is actually an extra set of outputs which show us the value that we've got in there. At the moment, it's all hidden. So what I'm going to do is I'm going to go back and so let's just delete that and add that in. I'm going to put it across the top because it's not necessarily for the necessary for the workings of what's going on, but it would be useful in terms of being able to see what's happening. Um, so program counter, program counter register. So in order to do that, I'm just going to tap off here and put some extra tags on so we can actually inspect the value of the PC register. And traditionally with binary numbers, if we've got them in a row, then if they're left to right, then they're as they would be written, but if they're vertical, then they're most significant bit at the top. So I'm just going to call this value 3 to 0 and rotate it. And then go back into the template. I'm going to do that at the top because then we can just plug those directly into LEDs to see what's going on. So notation. In fact, we needed to say value 3 to 0, which is great, which is exactly what we wanted. And then we need to link them up. So that's 3. Another reason for making sure we stick with some kind of convention for these orders is that it just makes it easier to do this kind of wiring up thing. Because it's hugely important that we wire the right tag to the right pin. Not because these pins are yet connected to anything, but because this labeling needs to be absolutely correct. Because then when we connect it up, we know we're connecting to the right thing. Right, so let's save and then go back to having a new circuit, dragging our program counter in, and we're going to need some inputs and outputs. What I'm not going to, yes, I'm going to do the bus because we need to check that we can do bus reading. So let's create a little bus for this first. And the way that I tend to do that is I have an LED at the top, a tag at the bottom, then link those up. And then I need a way of actually putting information onto the bus. So I use a tri-state buffer. And what I do is I leave a bit of a gap so that I can do a cut and paste and they just kind of fall into place. And then I'm going to put again another gap to help this process of cut and paste. I'm not going to cut that up because I need to connect all 4 of those together. And I'm just going to group select that, do Control C, Control V 3 times, and there's our bus. We need to just finish off this extra bit, which is to do the output enable for here. So this gives us the capability of putting a value onto the bus so we can read from the bus. And then we need to make sure we're connected to the bus correctly. Right, and we've got some inputs to do. So value isn't inputs. These fall down this side. 1, 2, 3, 4 inputs and inequality to inputs. And we'll also have 4 LEDs to see what the value being held is. Nearly there. I'm feeling quite confident. I feel as if we've got everything in that we should have. So unless I've wired something up wrong, hopefully this is going to be correct. So the first thing that happens when we press go is that the value starts at 1111. And the reason for this is because in the circuit that we've got for in the register, which then holds somewhere deep inside there, there's an SR latch, and that SR latch, when it starts, always seems to come uh, into the position where one is being held, and that's probably down to the order that we put I put the gates in. It might be different in yours because this is a simulated thing. So in when you do these things in hardware, this is a slight aside, but when you do these things in hardware, lots of things can happen at once because you've got lots of separate wires where things can be happening. When you do these things as a simulator, because it's a computer and computers deal with things sequentially, so it has to be turned into a sequential list of things that happen. Um, so a simulation, this is one of the biggest differences between a simulation and using hardware, is that there is some kind of order in the simulation that is not true in the hardware version. Um, and there are some things that are easier to do in the hardware to do with precise, very quick timing, because you can use the fact that gates have a slight delay to them as they go through, and this is by no means reliable in a simulator like this, as I have found. Which is why, if you know stuff about digital electronics, which is why I haven't been doing things like edge triggers and stuff like that, because it seems to, well, I've tried to get them to work in digital works, and it's beyond my knowledge and capabilities at this point. Anyway, that was a bit of a side. Let's clear our program counter so it should go to 0. So as we go ink 1, ink 2, ink 1, ink 2, ink 1, ink 2, it should start counting up ink 1, ink 2. That has not done what we expected then. Ink 1. Ah, I do know why. It's because we need to set that, and that will normally be set to high. Right, let's try again. Ink 1, ink 2. Yes! 1, ink 2. Yes, we're counting up. Ink 1, ink 2, ink 1, ink 2. I'm going to go through the whole thing. It's not that many because it's only 4 bits. And check that this is binary counting. This is a way of making a binary counter. Not the way that you choose, potentially, because there's quite a lot of stuff going on underneath. Yeah, we're nearly there. And then when we're at the top, it should overflow back to the start. Right. So the other thing we're going to do is we're going to check the data read. Interestingly, I've got output enable here. I'm not sure I'm actually ever going to use output enable from the PC. It just is a natural thing if we've got bus access to put that on. And I'm not going to take it off because this potentially makes this component useful in other CPU architectures. So, um, and because I have a habit whenever I've got bus connections to make sure I've got a bus read and output enable. Okay, so let's put a value in. Let's use 1010, one of my favorite binary numbers, which is 10. And so we need to do a bus read, and that should give us the 10. We'll disconnect that, and then we've still got the ink. So let's do our 2 phases and check that it's counting from there, which there's no reason why it shouldn't be. And then finally, let's just take off the ink and check that it's not incrementing. Yes, that's fine. It should be going round the 2 registers. It's just nothing's being added. So it looks like it's working. So we'll leave that there. And so I will get to say that's it from me for now.